Okay. Are we ready? So we'll continue with the stereoisomers. Okay. So you all can solve it at the same time. Tell me now, how many stereoisomers do we have in this one? And how many stereocenters do we have? Stereocenters, chiral centers.
Can we break it?
Oh,
Sorry?
for stereo center.
We have 3.
3 stereocenters? No, stereo, not stereoisomers, stereocenters. 2 stereocenters,
Yes.
right?
Oh, it's
Absolutely. So if I told you that what you need to do with these, you need to open them up, right? So if I see this one, what's wrong? Okay. I know that here I have always, what's wrong? Okay, if we have structure like this, so the part which is basically, okay. So if we have structure like this, so the part, this one is always CH3, isn't it? Methyl group is always, if there's nothing, so we have a methyl group over there. So here we have OH, okay, and here we have NH2. Here we have double bond O, and then we have OH. Can we have this as a stereo center?
which one? No.
Why not?
It has 3H.
It has 3 H's,
Because
right?
H.
Absolutely. So it's not eligible at all. We will omit this. Okay, can we have this carbon as a stereo center? This one?
Because we have
No, because it has a double bond.
Absolutely. So you'll forget about, whenever you see double bond, forget about that, right? Then we move on to this carbon. Can we have this carbon as a stereo center? Yes. How? This side we have what? NH2. This side we have, what's wrong with it? Yeah, we have 4 different groups. Okay, if you see here, we have a different group over here. Okay, and what do we have? We have a different group over here. And this side we have hidden hydrogen, remember? Hydrogen is always hidden. Don't ever forget the hidden hydrogen. So that is why it's recommended to open the structure, right? And always remember that you have to satisfy the tetravalency of the carbon, right? So that is why I was able to find out that there was one hidden H over here, okay? So there's 4 different groups. So this is your one stereo center, and this is your another stereo center. So how many stereoisomers? 2 raised to the power 2. So I can have 4 enantiomers, or you can have 2 pairs of enantiomers, you can say like that. Now I want all of you to do the next one. You all can do, ladies, next one. You can share the screen if you want to, or take a picture and send me on my on the chat window. Solve this and tell me which are the 2 stereo centers or 1 stereo center. Yes, Monira, where's your pencil and copy? In biochemistry, you should always get pencil and copy. We need to do, yeah, thank you. Online ladies, are we solving?
Yes, doctor.
3, what do we have 3? 3, you mean the 3 stereo centers? 2.
Yes, 3.
3 stereo centers, how come?
I only found 2.
How many, Dania, the question D part, which is on your screen right now, you need to tell me how many stereo centers are present in the molecule which you see on your computer right now. Dana. Two stereo centers or stereoisomers? The 2 different things, Mohammed. Are you talking about stereo centers or stereoisomers? Aileen, how come we have 3 stereo centers? Can you please explain? Mohammed says 2.
Teacher, because NH
Uh-huh.
and HO and the second HO, so it is 3.
No, absolutely wrong. No, no, no.
There's
Mohammed,
one stereocenter.
yes. And can you identify which one it is?
NH2.
The carbon which is attached to COOH, NH2,
Absolutely.
another carbon and hydrogen then.
Absolutely. Very good. Thank you. Thank you. What about you, ladies? Tell me. Oh, you're not in the last class? Oh my God. You know, you have to come and meet me then. You will be lost in this then. Don't worry. You can come and meet me. No, 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 no. This cannot be there. No, no, no. Yes. Yes, tell me, Shuk. How about you? Show me a copy. Show me your notebook. Show me your notebook. Okay, very good. Okay. Very good. Super. Absolutely very good. Yes, Munira and Lara. What do you think? Which one? No, you always mark stereo center with the asterisk, no? With the asterisk mark? Ah, okay. You always mark. Can you show me where is it? No, 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 not at all. Not at all. No, 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 not at all. How about you? Mohammed. Abdul Rahman. NH2, you mean to say? This one?
Yes.
Yes, absolutely. Good. Okay. What are we looking for? Right. We're looking for a carbon. We're looking for a carbon which has 4 different groups attached to it. How can you say that this is a stereo center? This cannot be a stereo center. What's wrong with this today? Ladies, my computer is giving me trouble. So tell me, how did you say that this is a stereo center, ladies? This cannot be a stereo center. We're looking for a carbon which has 4 different groups. Okay, if you remember, I told you whenever you have something like a double bond over there, that's not even eligible. You're looking for sp3 hybridized carbon, right? So there's no question that this, or anything, because we have a double bond over here, and here we have OH repeating, right? This cannot happen. Yara, why did you say this one? We have a double bond over here. This cannot be, right? So if you see this carbon, got it? This carbon, we have H over here. Shh. Yes, somebody was not on this one. This one. Sorry, guys. This one. You were showing the same one?
Miss, can you break it? Can you break this?
This one. Sorry, this one.
Yes.
If you talk about this carbon, it has always hidden H's, right? So can this be? You cannot say this is a stereo center. Why? Because if you see here, this is one, right? It is same H. So we want something where we have 4 different groups attached to it, right? So if I see this carbon on this side, what does it have? This side, what does it have? What does it do? Okay, this side, this whole thing. Okay, let's say this, and we already know that carbon is tetravalent. Yes, tetravalent. So this is H, right? So this is not, right? This is not. This is not. This is not. So we have only this carbon. Are we okay, everyone? Can you solve the next one now? I want to see both of you. Okay. Okay, let's do the next one, guys. E1. I want everyone to solve this and tell me. We all are solving E1.
Doctor, there is none.
Sorry?
There is none.
I'm sorry. There is one. There's one. Okay, no.
No, I said there is none. No
None.
stereo center.
How do you say that? No stereocenter. How do you say that? Did you open the structure? Did you open the structure? Dana, how do you say that? None. No.
Yes, I couldn't find one.
Will try one? Try once again.
Doctor, there's two.
Absolutely. Can you identify the carbon number?
The one attached to OH and the one under it attached to the 2.
Absolutely. Munira. Yes, thank you, dear. Thank you. Can you?
I didn't find.
You didn't find it?
I think this one.
Okay. Which one? Which one? This one or this one?
This one. This one.
Which one? No, it has. It's a methyl group.
Yes.
No. Okay. Okay. Good. Okay. Wonderful.
Is it correct?
Yeah, yours is correct. Absolutely. Shug, what about you? How many it has? You did? What about you, Yara? Were you able to find it?
Yes.
Okay, very good. You're opening it up. Very good. Opening it up will definitely help you. So you want me to open it or?
Yes, please.
Okay. If I open it, I know that this is one carbon. What's wrong with this? Okay, let me make it a little bigger. Okay. So start satisfying the valency. Carbon has always
H.
an H, right? H and H. I want 4 bonds for the carbon. Isn't this carbon having 4 bonds? 1, 2, 3, 4. 1, 2, 3, 4. Correct?
Yes.
Am I correct? Okay. This side it has OH, and this side it has H. This carbon has H. This carbon has H. Am I correct?
Yes.
Okay. So this side it has this whole propyl group. Okay, we have 1 carbon here, we have 1 carbon here. Okay, and I have 1 H on this side. So this carbon has its own share, right? 1, 2, 3, 4 bond, right? And this carbon, H on this side, H on this side. Did I miss something? And this, and whenever something is hanging, you know that it's always what? The end part is always methyl group, right? So if you want, you can open this as well. You can have 3 hydrogens, H, H, H. Right? And this one will also have H. Now let's start. Everyone, please look at the board, everyone. Yara, can this carbon be my stereocenter? Why?
Because it has 2 hydrogens.
2 hydrogens, so it's not even eligible.
Yes.
Can this carbon have? Not even eligible. This carbon? Not eligible. This carbon?
No.
We're looking for those carbons which have at least what? 1 hydrogen or less. Can we have this carbon?
CH3, CH3.
No, it has CH3 on this side, CH3 on this side, so this carbon is not even eligible.
So give it to the one with OH.
Yes, so this carbon, if you look at this, on one side it has what?
OH.
OH, other side it has H. And now I want to show, look at this. So this side it has OH, this side it has H, okay? Now I'm going for a walk. As I go for a walk, I take this pathway. What do I see? I see CH2.
Yeah.
If I go away with this pathway, I see 1 more CH2. Till now they're same. So what is my job? I'm going to look for, I'm not going to stop till I find a difference. I'm moving further down. What do I have? I have 1 more CH2. If I go down, what do we have? Do I have CH2? No. What do we have? We have a whole propyl group attached to it. So I found a difference. So automatically this will be my 1 more group. And this will be my 1 more group. So that means this carbon, let me erase this. So that means this is my 1 stereo center. And if I look at this one, I have hydrogen on this side.
Yes.
I have this whole group on this side, right? And then again, as I said that, we'll go for a walk. I move on right-hand side, I meet what? CH2. I go on a walk on the left-hand side, left lane, I take 2 lanes. This lane I have also what? CH2. We have to continue walking till we find the difference. I go forward, what do I see? I see, oh, this has OH group attached. Do we have OH group here? No. So, khalas, this is your two different groups. Isn't it easy now?
Yeah.
Opening up will help. When you begin with, opening up always helps, okay? And don't forget to put the required amount of hydrogen, and then it's all okay. Then it's definitely very easy after that. Clear? Yes. You can do this one now.
We need these two, right?
Now,
This carbon and
this. See, you learned it now. Very good. Very good. Absolutely. You learned it now, right? Munira,
Yes.
isn't it? Online. How many stereo centers do we have?
There's 2 stereo centers.
2, Professor.
Thank you. Is it clear, Dana, now? Dana, how many stereo centers? Is it clear, Dana? Thank you, dear. Thank you. So similarly, you can, as I said that, maybe at the end of the class, I'll show you when you buy your access code, where to find, many problems to solve it, okay? But I can give, I can plan something, maybe I will upload some more problems so that you can, practice. Or you can practice, you will find so many molecules. Go ahead and start practicing. There's so many chiral molecules, okay? So with that, we finished how to identify. Okay, tell me this one. Online and in class, girls. How many stereo centers for this compound or this molecule? 4 stereoisomers, Faiza. Aileen says 2. 2, show me. Which one, which carbon?
One with an extra, I didn't check mine.
Okay.
Yes, and another one with
See, you're expert now. Yes, anybody else? How many in this
Yes. Also 2.
There are 2.
There are 2, absolutely.
Teacher.
So this is not even eligible. Oh. Why is it giving me trouble today? Okay. This one is not even eligible, isn't it? This carbon has a double bond. This methyl is not even eligible, isn't it? It has 3 hydrogens. Okay. So this one, let's think about this. There is NH2 on this side. If I take this hydrogen here, so hydrogen on this side, this whole group on this side. If I take this hydrogen here, right? OH, hydrogen, this whole group and this whole group, right? So I have one this, another this. 2 stereo centers and 4 enantiomers. Correct? Okay. So definitely this is a structure of the cholesterol. We will not give you, then for 1 hour you're solving the stereo, only one question for the stereo centers. You'll not get questions like this, definitely. You'll get the ones which we practiced, right? Something like that, but not the same ones, of course, the different ones, right? So you will not get something like this, okay? This is basically a structure of the cholesterol. Look at this, it has 8 stereo centers. Okay, so these many stereo isomers. But do we have so many enantiomers in our body for cholesterol?
Yeah.
Do we have so many enantiomers in the body for the cholesterol? No. Can you believe? Can we have 256 stereoisomers in the body? No ways. This is the best part about chirality. Even if you have many enantiomers or you have many stereoisomers, only one is active in the body. Your body is basically very clever. They don't want to waste time to make so many structures. This is the best part about the nature. In our body, for example, even if you find, for example, 4 enantiomers for a particular polysaccharide, for example, all 4 will not be active. Only one will be active. Okay? So this is basically a law of nature to conserve the energy, not to waste the energy. So with that, we finished the enantiomer part. Okay, we move on to the diastereomers. Diastereomers, you will practice more in the next chapter. The next chapter which we're going to start is the carbohydrates. Okay, so just have a brief introduction about the diastereomers here, so that you know the difference between an enantiomer and the diastereomer. What is the basic difference between the two? Okay, so you know that in enantiomers we said that they are what? What is the criteria for the enantiomerism? Point number one, they should be enantiomers. They should be mirror images,
Mirror
right?
images.
Thank you. Non-superimposable mirror images. Asymmetric, very good. And the third thing is they should have at least one chiral center or a stereo center. Okay. Now, let's say we have a molecule which has more than one stereo centers. Okay. If you see this, how many stereo centers can you identify in this? What do you think? Online ADs, how many stereo centers can you see? Let's say in this one. Let's say in this one. A. 2. Who said 2? 2. Munira, you? Can you identify? Very good. Which one? Online.
2 also. The one on top and the one in the middle.
Absolutely. If you see here, this is my one stereo center. One group, another group, and this whole group. Can I say that? Yes. Absolutely, I can, right? So this is my one stereo center. And let me erase this. And if you see, this is my another stereo center, right? One group, another group, another group, and another group. So how many stereoisomers can you expect here? If it has two stereo centers. So 2.
Or
Yeah, very good. So you will have 4 stereoisomers, or you can say you can have 4 enantiomers, right? Now, when you have situation like this, what can you expect the relationship between all of them? I know the relationship between A and B. If I look at them, if I put a mirror in between, What is A and B? A and B are
They are mirror.
the mirror images. Look at this. This has OH on the right hand side. This has OH on the left hand side. CHO stays there, CHO stays there, H here, H1 here, right? They're mirror images. And if you try to superimpose on each other, they are non-superimposable, definitely, right? What is the relationship between C and D? If I put a mirror in between, like this.
Mirror images.
Exactly. Again, mirror images.
Yeah.
Isn't it?
Yeah.
So C and D is my pair of enantiomers. A and B are my pair of enantiomers. Can I say that? Okay. Now, what else can I see in this diagram other than seeing enantiomers? Okay. If I look into this diagram, I see that this A and this C, are they enantiomers? They're not. They're not enantiomers, and most importantly, are they mirror images? They're not. So if they are not mirror images, but they are stereoisomers, right? So we call them as the diastereomers. So as of now, remember only one thing about diastereomers, that they are stereoisomers, definitely. Same connectivity, same molecular formula, but when we bring them in front of the mirror, right, they are not mirror images of each other. This is one of the very important criteria about the diastereomer. They're never mirror images. Forget about non-superimposable. They're not even mirror images, not at all. So we don't even count whether they are superimposable or non-superimposable. That's different. The basic criteria is they are not mirror images. So remember, enantiomers are mirror images. Diastereomers are Non-mirror images.
Doctor,
I'm not going to, yeah, yes, dear.
is this the cis and trans?
This one is trans. This one, yes. Yes.
Well,
Okay. I'm not going to further deep into this. And remember the only one point as of now, because we're going to discuss diastereomers and epimers again in the next chapter. We start with the carbohydrates. Okay. So the only thing which you have to remember is that they're never ever mirror images. Never ever. They can have more than one chiral centers, but they are never mirror images of each other. Okay. And what about other one? B and C. Again, diastereomers.
Yeah, diaster.
Look at them. They're not even mirror images at all. Right? So you can say diastereomers are also stereoisomers, but they are never mirror images of each other. It's like, if you remember, we have been discussing about hands, right? In chirality, we have been discussing right hand and the left hand relationship, right? So enantiomers, think like your right hand and left hand are enantiomers. Okay. If I make a handshake with Yara and me, Yara's right hand, my right hand, we are what? Diastereomers. See, her hand and my hand is similar, isn't it? She also has 5 fingers. I also have 5 fingers, right? But when we try to handshake with each other, we are totally non-identical. We are not even mirror images. Can you see this hand and this? Her, show me your hand. So we are not even mirror images, right? So we are diastereomers. Your friend's hand and your hand is a diastereomer. Your right hand and your left hand is an enantiomer. Are we all okay? We'll stop here. As I said that, we'll move on to the diastereomers again in the next chapter with the epimers and anomers and different other things. Now we move on to the optical activity. If you remember, I asked you last time, if you want to test whether this compound is chiral or not, what is the test for the chirality? I told you 3 things.
If it's symmetrical or not.
If it's asymmetrical, it's chiral. Point number 2, very good.
It is if it is superimposed or not.
Yeah, very good. If it's non-superimposable, it's chiral. The third thing was?
If it's attached to 4 carbons.
Yes, if it has 1 chiral center or it has 1 stereo center. Very good. Thank you, ladies. Thank you. So this is like a test for the chirality, and I'll give you one more test for the chirality and to find out enantiomerism is the optical activity. So we discussed last time enantiomers are the same physical chemical properties, only biologically they're different, right? So how do we separate them? How do we separate that this is R and this is S? How do we do that? Let's try to find out. Okay. We start with an ordinary light. You know what is an ordinary light? Ordinary light is a light which moves in what? In all the planes, right? It oscillates in all the planes, isn't it? That's an ordinary light. Plane polarized light is which vibrates maybe only in one plane, right? Only in one plane. So this is called as a plane polarized light. I'll explain you once again this. So polarimeter we'll talk about now. What is this polarimeter? And optically active we'll talk about these two in a minute. I want all of you to pay attention on this. This is a polarimeter. Okay. I want a blank page here. Give me a minute. Okay.
Let's just add a slide.
Yeah.
Now it's done.
Give me a minute. I'm trying to add this slide, guys. Wait a minute. We used to have a board here and I used to show it on the board, but anyways. It's not giving me an option to add this slide. It's all grayed out. Anyways, just leave it.
Teacher from here, the corner.
I was trying to look for a
The pen, yeah. You should use the pen.
no, not pen.
No, teacher, go down for the 3 dots. She meant on
The
the left
corner,
side.
corner.
Yeah, and then
No.
screen.
No.
Yeah, white screen.
White screen. Okay, thank you. So let's say I have an ordinary source of light, like a bulb, like this bulb, which is right now glowing over here. So in this bulb, I can have light in all possible planes. Can I say that? Can I say that? So this is a normal light, right? Wherein the light is oscillating in all the planes. What do? I take a polarizer or I take a filter like this. What is a filter? Or polarizer? Polarizer has strips like, slits like this.
Small openings.
Look at the perpendicular slits. Okay? These are what? Slits, and we call this as a polarizer. What is happening? What do you think? The light if I allow this light to pass through this polarizer, which plane of the light will it be able to pass through this? Can I? This one?
No.
This one?
No.
This one?
Yes.
Absolutely. So that means through this pole, it will allow only the light which is basically in this plane, the vertical plane. Only this light can pass through it. Yara, can you switch on the camera? Guys, I'm going to switch on the camera for a minute. Yara is helping us with that. Bring your hands on me.
I'll answer again.
You can enter again, yeah. Ladies, I'm switching on the camera. Give me a minute. Anybody else can, if you have, Munira, do you have it?
Yeah.
Please wait for a minute, everyone. Okay, can you come near to the table? And focus on my hands. Just a second. Back camera. You have to
You want to
mute. Right.
Okay,
Yeah, switch on the back.
this is the camera.
Is it? Yeah, they can see it. Is it?
Can you say, guys?
Can you all
No.
see everyone?
No,
Yeah.
doctor.
It shows that there's a camera option, but it just says Sabiq Qazi.
You have
Guys, you have to open the camera for Munira.
Munira, absolutely. Munira has,
I can see it.
everyone can see this.
Yes, doctor.
Okay.
No,
I still can't see it.
it's not Miss Sabia who's
Missing my name.
video. It's
Munira bin Muhawiz.
Make sure to change the view because it's actually showing for me.
okay.
Yeah, we can see it properly, right? Yes.
Oh, yeah. I just had to change the view. Okay, thank you.
Thank you. Okay. Now, if you look at this one, this is the source of light. Okay. Let's say this one is a filter. Okay, it's a polarizer. If you look at this polarizer, do you see slits over here? All these slits are vertical in shape. Okay, all these slits are vertical in shape. Look at this. Okay, and this is like my source of light. This is my source of light. Okay, so if this is my source of light, what's going to happen? Right? So what do you think? If the light will try to pass through this slit, right? This plane of light will not be able. The plane of light, which is actually, which is vertical, like this one, right? This one will not be able to pass. Look at this. This one will also not be able to pass. But the light which is vertical, this one is vertical light, right? Vertical plane, right? So this vertical plane, which basically looks like this, only this light can pass through these slits. So that means on the other side of the slit, I will have a light which is a plain polarized light. Look at the difference between the two lights. This light is basically in all the particular planes, okay? While as the light which I got after passing through the polarizer is only in one particular plane, and that is the vertical plane. Are we all okay?
Yes, doctor.
Is it
Yes,
clear to
doctor.
everyone? Okay, thank you. Thank you, Munira. You have to sit. I need to show later.
Yes.
Thank you, all of you. Yeah. Thank you. So that's what I was trying to tell you. In this particular, when I was having a general light, it had basically light traveling in all possible directions, right? But when I got a polarizer with the slit, it allowed only a light which is in one particular plane. And let's say here we have the vertical plane. Now, I have a sampler. Sampler will look like this. This is a sampler. Okay. So this is an inlet for the sample. I pour the sample from this inlet. And then I have one more. The way I had this polarizer, I had something called as an analyzer here, which also has what? Slits in the similar plane, vertical plane. Clear?
Yes.
So this and this is somewhat similar. Just as it was a polarizer, this is called as an analyzer. And I have my eye here, like I'm looking at it from this side. I'm trying to observe it from this side. What will happen to the light? Everyone, please pay attention. Now, I will first take a achiral molecule or achiral compound and pour this into my sampler. Okay. And allow the light to pass through it. What I see from when I stand from here, when I observe it, what do I see? I see the light which traveled inside. It's in one plane, right? It's a plane polarized light, right? The light which is basically traveling in one plane. This light was able to travel in the same direction, and I was able to see this light from here. What does this mean? The sample which I added, the achiral sample which I added to it, was this achiral sample able to change the plane of the light or change the direction of the light? The way the light was entering from here, exactly similar way, I was able to observe the light on the other hand side from the observer. Now I did something else. I replaced my sample. I replaced my sample now with a chiral compound. Second time what I did, I added, this was the first time. Second time I added when I added what I saw that when light was entering here, okay, I saw that filled with the sampler. And when I was observing it here, what I saw is that I had to rotate this, in order to see the light, I need to rotate it so that I can see the light, okay? When I rotated this analyzer, what I found is that this was the original plane of light, right? I saw the light was turned towards what? Towards what? Right-hand side, clockwise. Do you understand? Yeah. The light was turned, like earlier it was a plane. Look at my arm. Earlier the light was like this. And then now it has turned towards the right-hand side. So what did I infer from this? I inferred that the chiral molecule or a compound which is able to turn the plane polarized light. This is a plane polarized light, isn't it? Which is able to turn the plane polarized light towards the clockwise. I call it dextrorotatory. Now, this is like an old term. We used to write it as a small d, not a capital D, but now we've replaced it with the positive in the parenthesis. So all those enantiomers which have the capability of turning the plane polarized light towards the clockwise, we call those enantiomers as dextrorotatory, or simply we use the word plus. And the angle which is formed was, this angle is called as an alpha. I added another enantiomer. Third time, I added one more sample. I don't know what this sample is. But what I saw, my observation, when I rotated the analyzer, what I saw is that this time my light was turned towards left, anti-clockwise, counterclockwise. And I named that enantiomer as the levorotatory, or just the word small l, not the capital L, because you will see D and L we're going to use in carbohydrates again. That's a capital L. This is a small l. Okay, remember this. So we call those enantiomers as. So that means if I have two enantiomers, if I need to distinguish between the two enantiomers, I say that the enantiomer which is capable of turning the plane polarized light towards the clockwise, those enantiomers are called as dextrorotatory, or plus sign, whether we denote them with the plus sign, or those which are able to turn the plane polarized light towards the anti-clockwise. We call them as the levorotatory. Is it clear, ladies, everyone? Do we have questions?
Doctor, all of these two are chiral?
Yes. The first time it was achiral, nothing happened first time, right? Then the second and the third time I used chiral molecules. So only your chiral molecules or enantiomers have the capability of turning the plane polarized light either towards clockwise or towards the anti-clockwise. Any questions for me now?
Miss, do the levorotatory also form an angle alpha?
Sorry, I'm sorry, can you come again?
The levorotatory, do they also form alpha angle?
Yes, alpha angle. I forgot to show it there. Right, absolutely, very good. So it's like,
Okay.
this is my plane of polarized light. If it goes this way, it is what? It's dextro. This is my angle alpha. If they go on this side, the levo, it's like we can call it alpha dash, for example. Are we all okay? Any questions? So this is the diagram from your book. This is the the light, which is moving in all the planes, oscillating in all the planes. This is your polarizer. This is your sampler, where you fill the sample, and this is your analyzer, right? This one is your analyzer, and you're observing it here. Any questions? Yes or no, ladies? No questions.
Doctor, does this got anything to do with the R and S configuration?
No, very good question. I was about to say that, but I wanted to say that at the end. It has nothing to do with the R and S configuration. We can classify enantiomers based on R and S, right? We can classify enantiomers based on R and S, okay? Or we can also classify the enantiomers based on whether they rotate the plane polarized light towards the counter or anti-clockwise. It has nothing to do with the R and S. These are different ways by which we try to distinguish one enantiomer from the other enantiomer, because we don't have an option. We don't have an option because they all have same physical properties, same chemical properties, See, the boiling point, melting point, everything, solubility, everything is same. How will we separate them? How do we separate them? How can we distinguish them? Right? So this property is again shown by the what? Your enantiomers. So what is a specific rotation? Even though you just need to know this definition, but I'll show you the meaning of this definition. This definition tells you that whatever is the absolute, rotation, specific rotation of a particular enantiomer, okay, wherein it is equal to the whatever rotation we observed. Like, if you remember, I showed you something like this, right? This alpha, right? And the concentration, how much sample did I use? Okay, the concentration multiplied by how long was my sampler, the length of my sampler. I'm showing you this formula so that you know that what exactly this means. So you don't get confused. You don't have to remember this. You should know. That's exactly right. So this is like a specific rotation of what? Of any enantiomer. And if you see here, this 21 and D, 21 is a temperature. At what temperature did I carry this experiment? And D is basically what was my source of light. Usually we use the sodium lamps for this. What was my source of light? But you need to remember the definitions you see here. Is it clear for everyone?
Yes.
Okay. Then that was all about how your enantiomers can turn the plane polarized light, whether they're optically active or they're optically inactive. Okay. Now, there's something called as racemates. What are racemates? If someone will ask, what are racemates? Or racemic mixtures. Racemic mixture is like, if I take, for example, 50 milligrams of, let's say, one enantiomer A, let's say, of 2-butanol, for example, or if I take 50 milligrams of enantiomer, it's mirror image, right?
Yeah.
What do? If you take a mixture of like 50 and 50, what can you expect for the plane polarized light? Will it turn the plane polarized light towards clockwise or anti-clockwise? Ladies, question to everybody. Absolutely, very good. If you take equal concentration, 50 mg will try to turn the light towards what? Clockwise. And another 50 will try to turn the light towards the, so they will all cancel each other. So racemates will have optical activity 0 because they cancel out each other. So they have 0 optical activity. Racemates, the mixture of 2 different enantiomers. Online. Did you
Clear, doctor.
Okay, thank you, dear. Okay. And A chiral, I just showed you that A chiral do not show optical activity at all, because light, when I observed the light, it came out the way it was before, right? In the same plane. It was not able to change the plane of the polarized light. Now we'll talk about chirality of, we are moving towards the end of the chapter. We're going to talk about chirality of the biomolecules. Okay. So we know that, if you remember when we started this chapter, I told you why we are studying chirality. The reason is as we will start studying, carbohydrates, proteins, amino acids, nucleic acids, all of them are chiral. Biological system is chiral in our body. Right? That's why we're studying chirality. Okay. Then, if you remember, I gave an example of cholesterol. I told you it has so many stereoisomers, but only one is active. Okay. You might have heard the name of an enzyme called as chymotrypsin, haven't you?
No.
Right? No? How do you digest the food then? Chymotrypsin is the enzyme released by anybody? You're all studying anatomy. We're all anatomy students. trypsinogen. You've never heard about this? No. Online ladies.
No, doctor, never.
Muscles
Sorry,
in the trypsin only
your voice is breaking.
it in the actin and myosin.
No, not at all.
Doctor, what was your question?
The question was, what is chymotrypsin? Have you ever heard this name before?
It's in the stomach, I think.
Yes, which gland produces chymotrypsin?
I don't know.
Okay, it's a digestive enzyme produced by the pancreas. Okay, so I don't want to, we don't see the anatomy over here, but what is important is like this chymotrypsin is basically an enzyme which helps the digestion of the food, right? In our body. This chymotrypsin has almost 251 stereo centers. Can you believe? Stereo centers, 251. I can't even count how many stereoisomers are there. I can't even multiply them, isn't it? Can you believe? But only one of these stereoisomers are produced and used by our body. Out of so many stereoisomers, only one is active, which is able to interact with the required proteins. Proteins are also chiral, right? And then it helps in the digestion of the food. The idea is nature does not want to waste energy. It simply wants to conserve the energy, and that's why only one enantiomer is active in the body. Okay? Then we know enzymes are chiral. Okay? So I'll explain this at the end because I need to switch on the camera also. So once I finish, at the end you will switch on the camera. Okay? Once again, just be ready. Meanwhile, I will explain you this in a while, ladies, because I need to switch on the camera for this. So I'll move on to this one first. No, not now. Give me a minute. Let me finish with this. Within 5 minutes, I can finish this. And then you can switch on the camera. Okay? Munira. Oh. Now, chirality in biomolecules, as I said, that we know that. Other than that, we have chirality, like 50% of the drugs which we eat, medicines which we eat, show chirality. Okay? And for example, if you remember, we discussed that we have 2 isomers or stereoisomers of ibuprofen, R and S, but out of these 2 only S is active, which acts as a painkiller, like anti-inflammatory, while as R is inactive.
There's always S active.
No, that was I was about to say that. It's not always S is always active and R is inactive. You will see that it depends upon, sometimes R is active, S is inactive. Sometimes S is active, R is inactive. Sometimes R is a painkiller. It depends on the molecule. Sometimes R is a painkiller and S is we'll discuss that. S is a carcinogenic, cancer causing. Not necessarily that, 2 enantiomers are always safer for the body. It depends how they react within our body, in the chiral environment in our body. I'll give you a story of have you ever heard the thalidomide tragedy? Never? Okay. Thalidomide was a drug which came around, I think in 1956.
Yes, I hear about it.
You heard about it? Thank you, dear. Thalidomide was a drug, okay, in Germany, okay? And this was basically used as a sedative. You know what a sedative? Makes you sleep, right? And then what happened, and it was soon realized that this drug cannot only be used as sedative. Females can take this drug when they're pregnant, especially in the first trimester, okay? And females have that morning sickness. They feel like vomiting, okay? Irritating nature, vomiting, right? Nausea. So what they did is like, they said that, okay, doctors started prescribing thalidomide as, you can take this drug for your morning sickness. It started with Germany, and soon it moved to Europe, Australia, and different other countries. And every doctor used to prescribe thalidomide for all the females, and it used to help a lot. Female used to feel very relaxed with no vomiting and nothing. Then one fine day, after 1 year, they realized that almost 5,000 to 7,000 children who are born with those females who took the thalidomide, they have a problem with what? With no limbs or shorter limbs. And soon, and it was like throughout the world, everybody knew about, oh my God, what happened? By 1960, thalidomide was completely banned. It was sold as a racemate. Now you know what is a racemate, right? Racemic mixture we just spoke about. So it was sold as a racemate, and 1960 it was totally banned. Because like imagine by 1960, almost 10,000 children were affected with the thalidomide, and 50% of them died. Only 50% were survived, and look at it, they're all saviors of thalidomide tragedy. And then researchers started finding out what is happening, why did this happen? They found out that thalidomide, one enantiomer of thalidomide is good. One enantiomer of thalidomide is absolutely good. It cures what? Morning sickness. Other enantiomer is not good because it is the teratogenic, which has a capability of causing what? Birth defects. Same molecular formula, same connectivity, same structure, same physical, same chemical property, but the way they react in our body is different. It was totally banned, this drug. And then the pharmaceutical companies, they came to know that, oh my God, this can happen. They used to make a drug as a racemate, halas, give them as a racemate. Now that FDA made, very strict guidelines saying that no doctor will prescribe a drug, or not only that, the pharmaceutical company should make a drug and they should know that whether it's R or it's S. Give the structure of each enantiomer, because we now know that we used to think that it's one compound, nothing will happen. That's why I told you, 2 enantiomers are not like one compound. They're 2 different isomers. They can react 2 different ways in our body. Look at this. You understand? Yes. And then it was totally banned for 40 years. I think 2006, they started again using thalidomide, but they have found its anti-cancer properties. It can be used against breast cancer, but the doctors have been strictly told that you should not use thalidomide to the pregnant females. Pregnant females should not take this drug. It's again circulating in the market, but not like in a big way. Okay.
Doctor,
Yes.
does it affect future pregnancies?
It's basically the person who ate thalidomide, it's affecting only that pregnancy. It used to affect. Nowadays, no doctor can prescribe thalidomide to any pregnant female. Okay.
Okay, thank you.
Okay. And same thing. I'm just trying to give you examples that how 2 enantiomers are with 2 different things. Look at this. We all eat naproxen as a painkiller. If I have a headache, I sometimes eat naproxen, right? We all eat. The S enantiomer is what? A very good painkiller. The R enantiomer is a liver toxin. Can you believe? That's how it, at the same, exactly. 2 different enantiomers. If we talk about the limonene, the positive, what is positive now? Dextro or levo? Positive is it D or is it L? D, right? So limonene is an enantiomer which is found in the oranges. It's another enantiomer gives taste to the lemons, 2 different tastes. Yeah, isn't it? Or you have the tritiquinol. One enantiomer is a bronchodilator. It opens what? The smooth muscles in the lungs. If somebody has asthma. Other enantiomer inhibits the platelet aggregation, prevents the heart attack and strokes. It prevents the clotting of blood, like your aspirin, right? So these were just few examples which tell us that don't treat your enantiomers what?
The
Same. They're basically 2 different things. Munira, be ready. So that is why now drug companies try to make now pure drugs, but it's very it's very costly for drug companies to make a pure drug. It's very costly for them. But now they have to, okay? Or levodopa, you might have heard that earlier we eat levodopa. Only that part, that one is active. The levodopa is active because it treats the Parkinson's disease, these tremors. The other one is not active at all. Okay? So these were a few examples. As I said, the chapter is about to finish, and this is the last slide which we have to discuss. Chirality of biomolecules. Okay, Munir, are you ready? Yes. Okay, so here we're trying to show you that we just told you enzymes are chiral, proteins are chiral, carbohydrates are chiral, nucleic acids are chiral, right? And then when they react with a substrate, they have to match their stereochemical requirements. What does that mean? For example, we are doing the chapter endocrine system. What do we say? We said, okay, thyroid hormone is produced by the thyroid gland, but it should go and bind to its target cells. The target cell can be any cell in the body, right? But that target cell should have a receptor. Why would thyroid hormone bind to the receptor? How? Or why do we say only one enantiomer can bind to the particular enzyme? Why not the other enantiomer? Because every enzyme is a stereo-specific to its substrate. That means, for example, every key cannot open all the locks. Every one key is for one particular lock. You understand? I'm going to show you something here. Can you come, Munira? This is like a last slide which we're discussing. We're discussing the stereospecificity between enzymes and the enantiomers or the chiral molecules. She's switching on the camera, ladies. She's helping us. Thank you, Munira. We will again switch on the camera for Munira. It worked earlier.
Yes, it's open. We can see.
Okay, let me see. Give me a minute, guys. Where is Munira? Yeah, here it is. Okay. I'll show them this one. You all can see this, right? Yeah. Okay. I have two enantiomers here. And what I'm trying to show you is that why do we say that only one enantiomer can bind to its receptor? Munira, please pay attention. Okay. So let's say this is my enzyme. Look at this enzyme. It has specific sites to which only specific atoms or molecules can bind. Look at this. This is circular in shape. This is square in shape. This is triangular in shape. Look at this. I have two enantiomers. Do you see this? Okay. Look at this. The circle one is going to the circle one, the square one into square one, and the triangle one to triangular one. Look at this. That is how when we talk about receptor, let's say when we discuss the steroid hormone and its receptor, right? So that's how your enantiomers or your hormones bind to or your enzymes bind to the receptors. This is like one enantiomer, okay? Why do we say that one enantiomer is active, another one is not active? And I try to put this enantiomer now. What do you think? Online ladies, what do you think?
It can't fit.
It cannot fit. The circle one is fitting, but what about the square one and this one, right? It cannot fit. What does this prove? Thank you, Monira. What does this prove? Online and it proves that whenever we have a particular enantiomer, as you can see here, there's a glyceraldehyde here. Glyceraldehyde has CH2OH, it's oval in shape. This is a carbon here. This is hydrogen here. This is oxygen here. This is hydrogen here. This is aldehyde group, and look at the shape. Okay. And if you look at this, this is the enzyme surface. Okay. When the enantiomer binds to it, right? So CH2 has its own what? Substrate site. H has its own like an oval thing, small oval thing. This one has a circular thing. O. The hydrogen has a oval thing. So this is totally made for each other. It fits completely, isn't it?
Yes.
But let's say you have another enantiomer. Look at this. Why do we say this will not fit? Because it is oval in shape, and I have on the substrate, I have a place for the square or cube, whatever, cuboid, whatever it is, right? So this will not match, these will match. So that is why we say one enantiomer is active in our body, another one is. Yes, that's all for today's chapter with with the chirality chapter. We finished the chapter here. Question time. If you have questions, please ask me questions. Yes, dear.
You said that one enantiomer could be toxic. Okay, but how come if it's not going to enter the surface or the inside surface? How come it's gonna be toxic?
It has some other receptor in the body.
Oh, okay.
Got it? Not the same one, some other receptor, where it is producing toxicity. No questions? Why everybody?
Doctor, I have a question.
Please go ahead.
When you were assigning stereocenters, you said they were supposed to be attached to 4 carbons, right?
Yes, absolutely.
And then there was one question where it had CH3. Why did we not count that one?
Because CH3, C is attached to how many hydrogens? 3 hydrogens, right? If you have something like this, if you have CH3, if I open this structure, this is going to be what? 3 times H, right? Is this carbon my chiral carbon? Run.
No.
It's not, right? What is the criteria for what is the criteria for these stereocenters? It should have 4 different groups. So it has 3 atoms which are H, H, and H. So that's why it doesn't qualify stereocenter.
Okay, I got it.
Got it? Okay, dear.
Yes, thank you.
Thank you, dear. No questions?